Welcome to lesson 3 from chapter 9, Pure Mathematics, all about differentiation. Today, you're going to be introduced to an idea known as the product rule. So this is going to be another rule that's going to go in our differentiation toolbox that will allow us to differentiate even more functions and expressions. I'm giving you some standard results that we've learnt already that we're going to be referring back to quite regularly. So without further ado, please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the solutions. Now, question 1 is a little bit different than what we're used to. I've given you, 3 derivatives, 2 of which I've actually done for you. And the third one you have to infer from the 2 previous examples. So I'm asking you to be pattern spotters, essentially. It's the essence of being a mathematical problem solver, isn't it? So the first one, if you look at it, it's x cubed multiplied by sine x. So this is what we would call a product of 2 functions. And this is the essence of the product rule. I would like to differentiate that expression, x cubed sine x. Now, I've given you the answer. This is correct. And the question is, what is going on with this derivative? I mean, you would expect a naive approach, of course, using the skills you've already got, would be to say, well, if I differentiate x cubed, I'm going to get 3x squared. And if I differentiate sine x, I'm going to get cos x. And there's nothing wrong with that. I mean, that would be a first step, wouldn't it? That would be a natural thing to do. It's not correct, but you can see that although this is an incorrect statement, we do have the 3x squared as a feature in our answer. And we also have the cosine x, the cos x, over here in the second term. So the question is, what is going on? Well, let's take a look at the second example and see if we can go a bit further. So once again, I've got the product of x to the power 4 and the cosine of x. Okay. Now, if you look at the expression on the right-hand side, this is the actual derivative. We have the 4x cubed written first. That's the first thing that we see. But it's been multiplied by the cosine of x. So it looks as though I've got the derivative of the x to the power 4 here written here. So they coincide. Okay? The derivative of the x to the power 4 comes first. Then we've got the cos x, and we just keep that as it is. So this cosine x just stays as it is and goes in the second position. And then we've got a negative. Now, the negative, we'll worry about that in a second, but we can also see that we've got the x to the power 4 appearing again, all right? And this time we've got a sine x. Now, we know that if you differentiate the cosine of x, you will get a negative sine x, all right? So if I just sort of make a little list of what we've got, it looks as though we have x to the power 4, which we know differentiates to 4x cubed. We've also got the cosine x, which I know differentiates to negative sine x. And then if I just put all the pieces together, I take the derivative of the first part, which is here, and I multiply it by the second part. And then I take the derivative of the second part and multiply that by the first part. So it's a case of swapping and adding, isn't it? And if I put all that together, I'm going to get 4x cubed cos x. And then if I add the x to the power 4 multiplied by the negative sine x, I seem to get that, which is exactly what we can see. So this is what I think is going on in this product rule. So let's apply this idea to example 3. So what I'm going to do, I'm going to list the functions. So we've got the natural log of x, and I've got sine x. Okay, and we can use our standard derivatives. I'm just going to do a short, I'm just going to put an arrow here just to indicate that I'm differentiating. So the natural log of x, as you know, differentiates to 1 over x, and sine x differentiates to cos x. Now, if I'm going to write down the answer, I need to pair these up. So I need to pair up the first function with the derivative of the second function. And I need to pair up the derivative of the first function with the second function. Okay, I multiply the two expressions that are the same color together and then add the result. So I think the answer to this is going to be the natural log of x multiplied by cosine x plus 1 over x multiplied by sine x. So I'm keeping all the yellow highlighted stuff together there, the first function and the derivative of the second function, and the derivative of the first function and the second function are multiplied together there. And that actually is the correct answer. Okay, moving on to question 2. We have been given a double angle identity, which we derived in chapter 6 or 7, I can't remember now. And we have to make sine squared the subject. Okay, well, that should be easy enough, I think. I think the first thing I'm going to do, I'm going to add 2 sine squared x to both sides. And you can do this in one step if you want to, but I'm just going to showcase some basic algebra skills here. Okay, so I've added 2 sine squared x to both sides. I'm now going to subtract the cosine of 2x as well. So therefore, we're going to get 2 sine squared x is identical to 1 subtract the cosine of 2x. So I have to subtract that. And to get sine squared, I need to halve everything. So therefore, sine squared x is identical to, and I'm going to do this term by term. All right. So if I halve everything, that's going to be a half subtract 1/2 of cosine 2x. Okay. Now that is actually, although it's just a simple exercise in rearranging an identity, that is a really important result you're going to see quite a lot, okay, from now on, as we embark on this this journey through calculus together. So just keep that sort of at the back of your mind. Now for part B, it says using your answer to part A and the standard result for the derivative of cos kx, show that the derivative of sine squared x is equal to sine 2x. Okay, this is a surprising result, isn't it? So the derivative of sine squared is sine 2x, and it says using this result. Well, that means I can replace the sine squared x with what I have in my identity. So that's really good. So I can replace the sine squared x with all this. Okay, so we're going to be differentiating that. So I'll just write that down as the first step. So this all implies that I'm going to differentiate. I'll put it in. So that's going to be 1/2 subtract 1/2 cosine of 2x. We'll close the brackets. Okay, and I know the standard derivative of the cosine of 2x because we did that in the previous lesson using the chain rule. Now, differentiating term by term. Well, if I differentiate 1/2, of course, that's just a constant. That's going to go. And all I've got to do now is concentrate on differentiating the cosine of 2x and multiplying that by -1/2. Okay, so I'm going to have to keep the -1/2 where it is, and then I'm going to multiply that by the derivative of cos 2x. Well, if you remember, the 2 is going to migrate out to the front, so this is going to be 2. Now, the cosine differentiates to negative sign, so it's going to be a -2 sine 2x. Okay, if you're not comfortable with that, just look it up from the work we did on the chain rule in the previous lessons. Right, now this is interesting. So you'll notice now we've got a half, or more accurately, negative 1/2 multiplied by negative 2 here. Okay, the two negatives will obviously cancel, and the half and the 2 are reciprocal, so that's going to just simplify to 1. So yes, indeed, we are going to get sine of 2x. Okay, now this is not a generalized rule, of course. If you differentiate sine squared, you don't automatically reduce this power down to a coefficient below. Okay, do not assume that. It's just an idiosyncrasy, I suppose you call it, of differentiating sine squared. Okay, so that concludes example 2. So in example 3, we've got exactly the same question, but we're asked to use a different technique. And I'm quite fond of attempting the same question from different approaches, so you can see how maths is unified. And this is calculus is really good for that. There's particularly with functions such as these, you can use loads and loads of different techniques here. So what we're going to do, we're going to use the substitution u equals sine x. Right. Well, first thing to do, I'm going to define an equation. We're going to say, we'll say let, first of all, let y equal sine squared x. Now, I already have my substitution that's given to me in the question here. So I just have to say, okay, therefore, y is going to equal sine, well, it's sine x squared, isn't it? So that's going to be u squared. Okay, so that's u squared. Simply because sine squared x just simply means sine x multiplied by itself. It's just the notation. We put the 2 after the n and before the x so that it doesn't look like the sine of x squared. Okay, because that's something different. Now then, now that we have y equals u squared, and we also have that the substitution u is equal to sine x. Now, the thing is, do we get the same result as previously? Well, we do our differentiation, don't we? So dy by du, this is using the chain rule. Okay, just differentiate with respect to u. That's going to be 2u. And using the standard result for sine x, du by dx is going to equal cosine x. Okay, now we put these derivatives together. So therefore, dy by dx is going to be the product of dy by du and du by dx. Okay, as we've seen several times. This is the chain rule, of course. Right, so we multiply these two derivatives together. Okay, so this is going to be 2u multiplied by cos x. So at the moment, it doesn't look anything like the answer. We've still got to substitute in the u, and you'll remember, please don't forget to do this. If your derivative is dy by dx, or if you're differentiating y with respect to x, your solution should be with respect to x. So it should have the x variable in it. We have seen situations where you can have the y variable in it as well, but there shouldn't be any u's in there. So the u here is the same as the u there. That's how we defined it. So I'm just going to rewrite that. So this is going to equal 2 multiplied by sine x multiplied by the cosine of x. So I've just made that substitution of sine x, u equals sine x there. It still doesn't look like the answer. So what have we not read in the question? Well, it says using a suitable trigonometric identity. Well, does that look like a trigonometric identity or something we've seen before? Well, this is why it's good to know these identities. You'll notice that this identity is a double angle identity for sine. So it's sine of 2x is identical to 2 sine x cos x, just a standard result. Okay, so it is indeed, we are fully entitled just to say, well, this is equal to sine of 2x, okay, as required. And you'll see we've got to the same answer, just using a different route, and we had to use a trig identity as well, which was nice. Okay, and the final example, we have question 4. We have a function defined for us with a restricted domain, x is greater than or equal to 1/2, and we have to find the derivative. Well, if you've done the exercises on the chain rule, this shouldn't be a problem. So the question is, what would the two functions be that we must compose together? Well, the f of x part, you'll notice this is just going to be 2x subtract 1 raised to the power 1/2. Okay, it's the square root, isn't it? Okay, so there is my substitution staring at me. I need to take out this part and replace that with u. So there we go. So let's do that. So this is going to be u to the power 1/2. And this is called fx this time. And u is going to equal 2x subtract 1. Okay. Now we'll use slightly different notation here. If you want to be consistent, in fact, which I probably should be, we'll call this one ux. So it's the function is called u, and it's a function of x. Okay, so I'll do that. Ux is equal to 2x subtract 1. Now let's differentiate everything. So f dash x. Okay, so bring the power down, subtract 1 from the power. There we go. And let's write it in surd form. Now I won't insult you. I know we've done this a few times. This is going to be 1/2 root u. Okay. And in the second function, u of x, so we'll call this u dash x. The derivative of that is just going to be 2. Okay. So we need to find f dash x, don't we? Okay. And I've just realized I've made a mistake here. This is wrong. I apologize. So this is a function of u, isn't it? Okay. So I'm sorry about that. So let's find the derivative f dash x. Now we're going to use the rather confusing looking definition for the chain rule here. You'll remember, of course, to differentiate f dash x, we multiply f dash of u and u dash of x. Okay, but the definition is, if you'll remember, I'll just write it down here. So this is equal to f dash. Okay, now it's ux like that multiplied by u dash x. You'll have seen it with g instead. So f dash of g of x multiplied by g dash x. It's just the chain rule. Okay, it's just the definition. But all you're doing is taking this part and this part and multiplying them together, and then you substitute the u back in later. That's all it means. So let's multiply these two parts together. So this is going to be 1/2 root u multiplied by 2. Okay. Now the good news is here well, I don't know if it's good news or not, but it's news. We've got the 2 there and the 2 there. They're going to cancel out. Or, well, they'll simplify down to 1. So that's going to cancel down to 1. So is that. So we're left with 1/the square root of u. Okay, so all we have to do now is substitute our u back in. So this is going to be 1/the square root, and substitute the u back in. So that's going to be 2x subtract 1. Like so. All right. So that concludes the warm-up. So now we're going to do some analysis of the product rule. Now we've had an idea of how it works. And the principle behind it is pretty simple. We want to differentiate expressions or functions that are clearly the products of two different functions. So it will become obvious with these examples. So if you can see x cubed multiplied by e to the 2x, okay, there's no way of differentiating those as one single function. That just can't be done. And similarly with 2x plus 1 cubed, we have a technique for that. And natural log of 5x, we have another technique for that. It's the product of two different functions. Okay, so the definition, as you can see here, is quite similar to the definition of a single function f of x from first principles. But now we have the product of two functions, f and g, as we define them in the definition. Okay, and the limit as h approaches 0 is the product of f when x has been substituted in with a slight change. So the increase in h as we did with f of x, and the same input into g, subtract the original product of the functions and then divide by h, and obviously take the limit as h approaches 0. Now, I'm going to show this idea just visually or just graphically first on a graph, and then we're going to use the analogy of areas of rectangles to sort of build a picture, because we are going to actually prove this in a moment. So I just want to go through the text just to explain how this works. So in the text, it says, suppose we wish to find the derivative of the product of two continuous functions f and g. Continuous is important, but you don't need to worry about it too much at this stage. So we're going to make a small increase from x to x plus h. Okay, so that's spilled over onto the next line, but it does say x plus h. Okay, now if we increase the input from x to x plus h, we will expect a change in the output, and we call the changes f of x plus h and g of x plus h. So I'm just going to use this idea on a graph just to show you, just for the case of x and f of x. So if we have an input, let's say, I'll just pick an arbitrary point on the x-axis. We'll just call this point x here. And we read off the value we're going to get. So this curve is obviously called y equals f of x. It's the equation y equals f of x. So the value I'm going to read off is going to be the value f of x. Okay. So it's my input. So notice my inputs correspond. Whatever my input is, I do f to my input, and that's the reading I get on the y-axis. Now what we're going to do is we're going to make a slight change. So I'm going to increase my x input by h, and I'm going to be arriving at some arbitrary point further along. So this could be the point x plus h, okay? Meaning that I have gone a distance of h between those 2 points. Okay, so that distance there must be, of course, h. H is small, of course. When we're talking in terms of calculus, where we have h or delta x or something like that, it represents a small, infinitesimally small change. Okay, so this is obviously exaggerated, but it's just to give you the idea of what's going on. Now, if we read off the graph, so clearly when I put x plus h in as my input, I'm going to get a completely different output, and I'm going to read that off, and this is going to be f of x plus h, because x plus h was my input. Okay, and you can see the correspondence there. So if I input x plus h, I get f of x plus h out. And you'll notice if we just think of them as measurements along the y-axis, you can see that the distance f of x, as you can see here, I'm just sort of going over it in red. Okay, well, suppose that's the distance, the size of f of x, size in inverted commas, there is a key difference, isn't there? So the f of x plus h appears to be a greater distance in this instance, okay? So we're going to use that kind of idea when we talk about areas of rectangles in a moment, okay? So just bear that in mind. And you can do exactly the same idea with G, okay? I've just chosen F just as an introduction to the idea of how the X input and the X plus H input affects the output, okay? So let's move on to the main task, which is we're going to build up a proof of the product rule. Okay, so the next bit is a task for you, and I would like you to pause the video, and you're going to find some expressions for the areas of the rectangles A, B, C, and D. So A, B, C, and D on the diagram on the right-hand side. So I'm just going to explain the process of what's actually going on here. So the rectangle on the left-hand side, okay, has an area of f of x, g of x, okay? The area would represent the product of f of x and g of x. So g of x obviously is defined here, and f of x is also defined in that first sentence just there, okay? Now then, if we make a slight increase to both sides, so this is where on the graph, as we've just seen, f of x is going to become slightly longer, longer again in inverted commas. This is an analogy, of course. So it's going to become slightly longer because we have now substituted in the input x plus h, which makes f of x plus h a slightly longer measurement. And you can see that over on the right-hand side. And if the same thing happens to G, what we get is a slightly larger rectangle. So the original rectangle, which you can see corresponds to A, so this would be rectangle A, wouldn't it, if you sort of cross-reference the diagram on the right-hand side. But we now, because we've made G slightly bigger, so the G of X has now become G of X plus H, as you can see down there. We've got a slightly longer rectangle, and we've created 3 new rectangles. And the same thing with f of x as well. We've now gone from f of x, we've made it slightly longer, f of x plus h, so we've obviously generated these 3 extra rectangles. Now what I've done is I've given you an expression for the area of C already. So it looks a little bit confusing, but I'll just explain what I've done. So if you notice, for C, if we just have a look at the dimensions of C, first of all, let's start with the vertical dimension. So this distance here, obviously I'm going to need that to find the area of C. Now, if you look at the distance, we know that the full distance of the greater rectangle is f of x plus h, okay? But the length of C is just going to be f of x, okay? Because it corresponds to that measurement there, okay? So we know that the height of C is, of course, just going to be f of x. So that's where this factor comes in. Now, the shorter distance, which we can see here, which I need, so the width of my rectangle, how does that come about? Well, that comes about because we've got this distance here, which is g of x plus h. That's the length of the largest rectangle, but we don't want the full length, so we need to subtract the length of this rectangle A. So the width of D is obviously the difference between g of x plus h and g of x. So that's why we've got g of x plus h subtract g of x here. So this is essentially, so it refers better to the diagram. So we've got the height of the rectangle, which is the f of x, multiplied by the width, like that. Okay, so what I'd like you guys to do, pause the video and have a go at calculating the areas of the other remaining 3 rectangles. Okay, so let's see if we've got the same answers. So if I'm looking at the area of A, I've already given that away, haven't I? We talked about that earlier. This is just going to be the product of f of x and g of x, because it's the same rectangle as the diagram on the right-hand side just here, okay? So we've already talked about that. Area of B, which is the thin strip on the bottom. Now then, if you look at the length of B, which I'm going to do first, that's the simpler bit. The length of B is just simply going to be g of x, isn't it? Because it corresponds to the length of A. They share the side. So I know I'm going to be having, for the length of B, it's just going to be g of x. Okay, so I'll put that in first. So that's the width. If I said the length, I meant the width, the horizontal distance. Now we multiply that by the slightly, well, the much smaller distance here, which is the height of the rectangle. Now the height of B is the difference between f of x plus h and the f of x that we've labeled already. So that's going to be the difference of f of x plus h and f of x. So I'm going to write that in. So f of x plus h subtract f of x. Okay, that's the thin distance, the height of the rectangle here. Okay, and what I'll do, just to make that easy, I'll put those in brackets. Okay, so we've done that one. C we've done, and D is the small rectangle in the corner. So what have we got going on here? Well, the height, of course, is going to be exactly the same as the height for the area of B. So I'll put that in first because that's just going to correspond exactly the same. So it's going to be f of x plus h subtract f of x, and we'll put that in brackets. Okay, and for the width, what have we got going on with the width? Well, let's have a look. So it's this distance here. Well, that's going to be the difference between g of x plus h and g of x. So I've actually got to write a product of two differences now. So I think I'm going to have to rewrite this so I've got a bit more space. So I'll write that in now. So this is going to be g of x plus h subtract g of x, okay, multiplied by f of x plus h subtract f of x, and it's the product of those two measurements, okay? So hopefully you agree with that. It doesn't matter if you got them the other way around, okay, but that's what you should have. All right, now the next bit, we found an expression for the area of the greater rectangle, f of x plus h, g of x plus h. Now it's quite a long expression, obviously, because there's so much going on. Now, if we just go through this step by step and make sure we've got all the key components here. So the first rectangle, so the first area is the area of A. So that's what corresponds to f of x, g of x. So I'll just make a note of that. So this is the area of A. Next up, we've got the area of B, which is this expression here, or this product. Okay, so that corresponds to the area of B. So I've done them in alphabetical order. Okay, so that's that one. And then we've got C and D. So just check your answers, make sure you agree with this before we move on to the next step. So there we have C. Okay, and then finally, we have D, which is obviously the small rectangle. So it's the differences between both g of x plus h and g of x, and f of x plus h and f of x. So let's just label those just for your notes. So that's the area of C, and that's the area of D. So we've got the area of the whole rectangle now. So what we're going to do next is we're going to use the definition from first principles of our product. Now, the definition was stated at the top of the page. So we know that the derivative, if I want to take the derivative of f of x, g of x, and take the derivative of the whole thing, we know it's equal to the limit as h approaches 0 of f of x plus h, g of x plus h. Remember, this is not a special definition. It's literally using the definition from first principles of any function f. It just so happens that this is a product of two functions, and we're substituting in the x plus h and the x as usual. So subtract f of x and g of x. Okay, so that's the original function all over h. Now then, this could get quite lengthy, so we'll summarize this, and we have the next step sort of waiting for us at the top. We know that the f of x plus h and the g of x plus h, which is situated here, okay, is obviously the same as this, which corresponds to what we have on the right-hand side. So without writing all that out again, we can see that in the numerator for our fraction, so this whole thing here, we're going to be subtracting f of x, g of x from all that. Now, if we do that, then we're just going to be removing the area of A, okay? And we'll be left with that residual area which was created by the increase of the input from x to x plus h. So I'm going to write that out. So I'm going to write out the box at the top minus f of x, g of x. So the area of A here will be gone because we are subtracting f of x, g of x here. So this is going to equal the limit as h approaches 0 of g of x multiplied by f of x plus h subtract f of x. Okay, bear with me with this. Plus f of x multiplied by g of x plus h subtract g of x. Okay, and then plus g of x plus h subtract g of x. Okay, and that's all multiplying the next difference, which is of course f of x plus h subtract f of x. Right, wow, so that's really long. Now all that is going to be divided by h. Okay, so put a really lengthy fraction in here. So all that is going to be divided by h. So what happens next? Well, remember we can use the idea of limits being a linear operator. So we've essentially got what looks like 4 separate terms here, which we can split up. Now, just going to show you how to do this in a quick kind of way. So without rewriting everything out again, you can see that the first term here, so the first term is a product of g of x and f of x plus h subtract f of x. This part here, if I divide that part by h and take the limit as h approaches 0, that is identical to the definition of the derivative of f of x, isn't it? Okay, and then similarly here, if I take the limit as h approaches 0, obviously this is divided by h as well. That's the derivative of g of x. So it looks like we're getting somewhere with this. So I'm going to put in a couple more steps and hopefully you can see what's going to happen. So this is going to equal the limit as h approaches 0 of g of x multiplied by f of x plus h subtract f of x. And this is all over h, okay, plus the limit as h approaches 0 of f of x multiplied by, and I should have put brackets around the first one really, multiplied by g of x plus h, subtract g of x. Okay, all that is being divided by h. Okay, and then we've got one more term. So we've got plus the limit as h approaches 0 of g of x plus h subtract g of x multiplied by f of x plus h subtract f of x. Right, and then obviously that is a product like that, and the whole thing is being divided by h. Okay, so just to reiterate what I've just said, in the previous step, the definition of the derivative of f occurs by having the limit of h approaching 0 and all this stuff. Now, what we could do is we could put in another step here where we can factor out the g of x, because that's not going to be affected by the limit because it doesn't contain anything to do with g. In fact, we will do that because I want to do this properly and it's being recorded. So this is equal to g of x multiplying the limit as h approaches 0. By the way, I used the same process in the video for the derivative of the natural log. So if you're interested in this stuff, this analysis stuff, please go and have a look at that video. It's in the playlist for differentiation as well. Okay, so there, I mean, that's indisputable now. We now have the definition of the derivative of f just by swapping the terms around, which we are allowed to do, of course, because the limit is a linear operator. Okay, same way a derivative is. Okay, and we can do the same thing for the second term, and then we'll talk about the third term in a moment. So this is going to be plus f of x multiplying the limit as h approaches 0. And this is going to be g of x plus h subtract g of x all over h, okay? And once again, there we have the definition of the derivative of g. This is exciting stuff, isn't it? So the question is, how do we deal with that final term? Now, we've spoken before about the limit of a sum being the sum of a limit or a pair of limits. Now, it's a similar way with the product. So if you have the limit of a product of two functions, then that's the same as the product of two limits. And this is essentially what we've got in this third term, albeit with a slight change, because we haven't quite got the definition of two derivatives here multiplied together, i.e. two limits. So this isn't g dash x multiplied by f dash x. And the reason is because we only have the one h term in the denominator. Now, if that was h squared, this would be the product of g dash x and f dash x, because we could divide the g of x plus h subtract g of x by h, and the f of x plus h subtract f of x also by h. And then the limits would be applied to both. Now, we don't have that, but what we can do is we can kind of force the issue a little bit here. So what I mean is we're going to assume, so I'm going to carry on this step. So this is the limit as h approaches 0 of g of x plus h subtract g of x divided by h, okay? Now, because I've used the h up in that limit, I am a bit stuck really with what I can do next. So I can't use the h again. So I'm gonna cheat a little bit here. So I'm gonna multiply this by the limit as h approaches 0. Now, I'm allowed to do this because the property of limits, as I've just said, the limit of the product of two functions is the same as the product of the two limits, which is essentially what we've got here. Now, we've got f of x plus h, subtract f of x. Now, if I divide this by h because I really desperately want to have that derivative, I can do that as long as I multiply one of those terms. It doesn't matter which one I do, so I might as well stick with this one. As long as I multiply one of these by h, okay? So I'm just going to do that here. So I'm running out of space a little bit. So I'm going to say that all that stuff in the green bracket, in fact, I'll go up here just to explain it. So all the stuff in the green bracket is going to be multiplied by h, okay? Now, if that happens, the reason I've done that is you can see that the h that I'm multiplying by and the h in the denominator will cancel, and then I've not got the extra h that I've invented. I'm basically multiplying by 1 essentially, which is not cheating, but it means that I can write it as the product of two derivatives. Now, I'm running out of room, so again, I'm just going to create a bit of space up at the top here because I hadn't anticipated this much room would be used up. So where are we up to? So for the final step, this is for the whole thing, we have got g of x multiplied by f dash x. Okay, so f dash x. And the f dash x corresponds to all the yellow stuff. That's multiplying the g of x all the way down here. Okay, then I've got f of x multiplying this box here. So this is, of course, g dash x. So that's good. That's multiplying g dash x. And then I've got the product. And this is the clever bit. I've got the product of g dash x and f dash x. Okay, and I'm going to have to get rid of this. Okay, now I've made my point. So maybe I could just put it further down below. So all that, remember, all this stuff here in this bracket is being multiplied by h, okay? So just to remind you of that, I just wish I had a little bit more space. Okay, so you can see, hopefully, I'm just going to highlight this a bit more clearly. So all that there, that's g dash x, okay, which corresponds to this one, okay? And all of this is f dash x, which corresponds to that. But in order for me to have written it in that form, I have to multiply it by h, okay? So I've got a h on the end. Right. Now, this is the issue. So the first two terms clearly give us the product rule, don't they, that we saw in the warm-up. Now, the third term, we have this h in it. Now, this can't happen, of course, because we have to take the limit as h approaches 0. So the h that I put in here, this is just sort of a dummy step in a way, because I just want to emphasize what's going to happen. If you are taking a limit as h approaches 0, then yes, you're going to have this here is going to be g dash x, okay? This is going to be this is going to be f dash x multiplied by h. But if you take the limit as h approaches 0, then this whole term is just going to go to 0 as well, because it's being multiplied by h. So that term there just goes to 0. So we are left with this. Now, this is the product rule. Okay, we've finally got there. So all that, make it look important, that is the product rule. So you can see it's the derivatives of both functions multiplied by their respective other function, and then you take the sum of the two terms. So that's what we saw in the warm-up. Now we're going to be applying the product rule to various examples so you can get used to how it works and how versatile it can be. Okay, so after that lengthy proof, you'll probably want to see the product rule, how it's given to you in textbooks. There's two main ways you'll see it. The way we've just derived from the derivatives and the rectangles, we write it as y equals f of x g of x. That's your function. So function is a product of two functions. So it might be a curve y is equal to f of x g of x. The derivative of the curve is given like this. It's the standard way of giving it in terms of functions. Another way you'll probably see it as well, which is really common. We call the two functions u and v like this. So y is equal to u v. Therefore, u is a function of x, v is a function of x. So you could also see it like this, where you would see y is equal to u of x, v of x like that, to be more precise. And then dy by dx would be the second function v multiplied by the derivative of u plus the first function u multiplied by the derivative of the second function v. Okay, those are the two standard ways you'll see the product rule. Now you can use the definitions if you like as they're presented there. So when you're given a question, you simply define your two functions f and g, or u and v, and then find the derivatives and apply the product rule. If you want a more shorthand way of doing it, I'm going to show you that in a second. So I'll do an example first and then lead you into a more shorthand way of doing it using labeling, which I find quite useful. Okay, and it also leads in nicely to what we're going to look at in the next part of this chapter, which is the quotient rule. So let's have a look at some of the examples of the product rule. Okay, so the idea of labeling is as follows. So in this example, I'm just going to write my function as, I'm just going to rewrite it. So it's going to be x cubed multiplied by e to the power 2x. Now, it should be fairly intuitive that the two functions are obviously going to be x cubed, and because I even said it, the way you say it even gives it away, doesn't it? So it's x cubed multiplied by e to the 2x. Now, the labeling idea is as follows. I'm going to label this first function 1 and the second function 2. So the first thing to do is we need to differentiate these two functions separately. Okay, so if I just write down function 1, we'll write them down separately. So this is going to be x cubed, okay, and function 2. So this could be your v or your g, depending on which way you want to do it. This is e to the 2x, like that. And then we're going to differentiate. So I'm going to call this the derivative of 1, d1, and the derivative of 2, d2. Okay, so if we differentiate x cubed, that's going to give us 3x squared. Okay, and if we differentiate e to the 2x, this is the e to the kx rule. So the 2 comes down, and then the function remains as it was. So it's 2e to the 2x. So it doesn't take long to find the derivatives. Okay, so now we can put the derivatives together using the product rule. So using the product rule, what we're going to have is, so remember we combine them diagonally. So we take the first function and we multiply it by the derivative of the second function, and we take the second function and multiply it by the derivative of the first function. All right, now the way I do it and the way I recommend you do it is as follows. You start with the second function, okay? So the second function is the bottom left-hand one. So it's this one. So we start here. So start with this. It doesn't matter if you don't, but you'll see in the next part of this chapter, it is quite useful if you follow the same procedure each time and start with the second function. So it's going to be function 2. So I'll write that in first. So it's going to be function 2, so that's e to the 2x, multiplied by the derivative of the first function. So that's going to be multiplied by first function, which is, of course, sorry, I beg your pardon, the derivative of the first function, which is 3x squared. And then we're going to add, it's always an add for this, we're going to add the other two that we've not used. So it's going to be the first function, which is x cubed, multiplied by the derivative of the second function. So it's going to be multiplied by 2e to the 2x. Okay, 2e to the 2x, like that. Okay, just check that you've done it right. So do the two yellow ones correspond? Yes, I think they do. So I've got the yellow one there and the yellow one there. That seems to be right. And then the two pink ones, this is how I've highlighted them. So it's going to be x cubed there, yes. And 2e to the 2x there, yeah, it seems to be fine. So let's just make this look a bit neater now. So this is going to be, we'll bring the 3 to the front. So it's going to be 3x squared e to the 2x. So it looks a bit better. And plus, we'll bring the 2 to the front, 2x cubed e to the 2x as well. And you could even factorize that if you wanted to, but we're not asked to do that. So that will get you full credit. Now then, the labeling which I've just used can be summarized as follows, and you can sort of say it to yourself like a mantra, okay, when you're doing it. So you can either say it as 2diff1 plus 1diff2, okay, as I initially did, or 2d1 plus 1d2. That's the product rule. So the d obviously stands for the derivative. So you can see I've got the 2. I start off with the 2 multiplied by the d1, and then I add 1 multiplied by the d2 here, okay, which is what I've done. If you do it like that, you won't go far wrong. So just remember, of course, that the functions f and g, and they could also be u and v. So that could be u and that could be v. Just label them as 1 and 2, and then away you go. So you'll probably just need to know some standard differentiation rules. Okay, so let's do a couple more examples using the product rule. And you'll probably find as well, as these get more complex, as the next one will do, you're going to get the chain rule built into these questions as well. Okay, so let's do the worked examples now. So for our first example, first thing to do is to write out what we've been given. So it's an equation with y as a subject. So that's 2x plus 1 cubed multiplied by the second function, which is, of course, the natural log of 5x. So you can see clearly that these are two distinct functions which form a product. So we have to use the product rule. I'm going to label the blue function 1 and the green function 2. These would all also correspond to f and g or u and v. Now, we'll just draw a little matrix here just so we've got the function and its derivative all ready to go so we can use the product rule. Now, if I just write them out, we've got 2x plus 1 to the power 3. So once I've done that, I'm going to have to find the derivative of that. And we'll call that d1. And then we've got the natural log of 5x, and I'll need to find the derivative of that. So we'll call that derivative d2. You'll notice, of course, we have to use the chain rule in both cases. The second case is more of a standard chain rule result, but the first one maybe needs a little bit of work. So I'm going to do some a bit of side work in the right-hand corner over here. So aside, we're going to differentiate big word, differentiate 2x plus 1 to the power 3. Okay, now to avoid confusion, obviously implicitly in this, you've got the functions f and g, which essentially are 1 and 2. We've also got y used already. We've got to find dy by dx, so I can't use y again. So I'm gonna call this function w, just so it's a letter we've not used. Okay, so I'm gonna set this equal to w. Okay, and then we're using the chain rule. I can just say, all right, if I had to differentiate w with respect to x, that would be a problem. But if I make a substitution here, I can make this look a lot easier. So my first function is going to be w equals u to the power 3. And then my second substitution, or my substitution, I should say, the function that is composed with w is obviously going to be 2x plus 1. Okay, so we'll do this using the chain rule now. So looking carefully at the variables, we've got w as my dependent variable and u is my independent variable. So to differentiate this is going to be dw by du. Okay, and that's easy enough. So that's going to be 3u squared. And then we do du by dx as normal, which is of course 2. So we have our two derivatives, and the chain rule says that we have to multiply the two derivatives together. So therefore, dw by dx, which is what I want to find. If I'm differentiating w and it's a function of x, then dw by dx is the derivative. So this is going to be 3u squared multiplied by 2. Okay, substitute the u back in, and obviously I can do the 3 multiplied by 2. So this is going to be 6u squared, which equals 6 multiplied by u, which is 2x plus 1. So we'll sub that back in. Okay, and that's all squared. Now, when you get confident with the chain rule, you might want to just differentiate all of this just by sight. So you can anticipate that the u is going to be the 2x plus 1. So you could think of that in your head as u cubed. You know the derivative of u cubed would be 3u squared. And then you just put all that back in. So you know it's going to be composed of 3 multiplied by 2x plus 1 squared. And then the only difference is that you have to multiply that by the derivative of what's inside the bracket. So the derivative of what's inside there is, of course, 2, which is why you get the 6 over here. So they're not actually too bad. Some of these are you can do in your head, all right? But maybe once you've got a bit of practice at it. So let's write down our result now. So we've got the derivative that we wanted. That was the awkward one, so we'll put that in over here. So this is 6. Oops, I'm on the highlighter setting. So this is going to be 6 multiplied by 2x plus 1 to the power 2. Okay, and you can notice the powers dropped by 1, which is indicative of differentiation. And then log of 5x, well, this is a standard result as well. So this is just going to be 1 over x. Remember that the 5 will cancel. If you use the chain rule, you will get 5 over 5x, and the 5's cancel. Okay, so now we're ready to use the product rule now. So I'll just box this off so we don't get confused. And so using the product rule. And what's nice about the product rule is once you've got all the constituents, those 4 constituents done, the 1, 2, the D1, the D2, we just have to stick them all together. So dy by dx is going to equal And remember what I said, start with function 2. So we'll always start with this one, okay, that I'm highlighting in green now, and then go diagonally. So we're going to go diagonally like that, okay. So let's write them all out. So dy by dx is going to be the natural log of 5x multiplied by d1, which is 6 multiplied by 2x plus 1 squared. All right, I'm just going to get rid of this. It's in the way. And then we're going to add. So there's an addition, even though it's the product rule, we have to add. And then we do 1 multiplied by the derivative of 2. So the mantra is 2 diff 1 plus 1 diff 2. So that's going to be 2x plus 1 cubed multiplied by 1 over x. 2 diff 1 plus 1 diff 2. Now then, can we make this look a bit nicer? Yes, I think we can. Don't need to factorize it. It's not a show that. We don't have to show it looks in a particular way. But if you notice, we can bring the 6 to the front, and I'll bring the 2x plus 1 squared to the front as well. Multiplied by the natural log of 5x. Okay. And then we can add 2x plus 1 cubed over x. All right, and that would be the derivative. Okay, finished. Okay, so now what's nice is we're going to revisit this sine squared question again for the 3rd time. And we're going to do it this time using the product rule. So we've used the chain rule. Well, we used a trig identity substitution and then a bit of chain rule, although it was a more standard chain rule result. And then we used the chain rule directly by setting sine equal to u and then y equals u squared. And now we're going to use the product rule to just verify that the answer is indeed sine 2x. Okay, so let's see what we get this time, and let's see which skills we're going to need and where this is going to take us. So if we use the product rule, first of all, I'll just define this as y is equal to sine squared x. And if this is a product, well, if it's sine squared x, of course, as we've already said, this just means sine x all squared, doesn't it? Which, in other words, means sine x multiplied by sine x. Hence, it is a product of itself. Okay, that's what squaring is, isn't it? So now we've got our 2 functions. So they are identical in this respect. So that's nice and easy. Once we've differentiated, it's done for both of them. So I'll label it 1 and 2 as usual. So this is going to be number 1. This is number 2. So 1 would be f, 2 would be g, or 1 would be u, 2 would be v, etc. So let's write them down. Got 1 and 2 there. And we're going to have sine x and sine x again. And using the derivatives, so this is going to be d1 here and d2 here. What do we get? So what are the derivatives? Well, derivative of sine is standard, isn't it? Okay, this is going to be cosine of x, as is this one. Okay, right, we can now use the product rule. So once again, just to remind you, we'll start with function 2. Okay, and then go diagonally. Okay. Yeah, don't go across, go diagonally. So using the product rule, what we're going to get, well, we just write it out. So we've got dy by dx is going to equal sine x multiplied by cos x, okay, which I've done in orange. I'll do it in orange again. And then add. So now we go back to function 1. Sine x multiplied by cos x again. So this is sine x multiplied by cos x. Okay, so this is going to generate the same term twice. So it's quite simple what we've got now. This is just going to be 2 lots of sine x cosine x, or 2 sine x cos x. Right, now we have to show that the derivative of sine squared is indeed sine 2x. And once again, if you just go up here, we can see that we've got a double angle trig identity. So since we know that sine of 2x is identical to 2 sine x cosine x, we now know that if you differentiate sine squared x, you're just going to get that. So that's another nice way of doing it. So we've got the final result. And I would strongly recommend you practice this. There's a nice exercise to follow. Do as many of those questions as you can. Get the product rule, part of your skill set, part of your toolkit. And then next time we're going to look at the quotient rule.